everybody, and welcome back to the series on differential equations. Today we're going to continue our exploration of first-order differential equations, in particular several equations that are going to be nonlinear, and classify them as either being an exact differential equation or a non-exact differential equation. As you probably can already guess, we are going to establish some solution strategies associated to exact differential equations, and also at the end we'll discuss a few scenarios where we can actually turn non-exact differential equations into exact, as long as that particular structure of that equation has some particular geometry, right? All right, so first off, what does it mean for a differential equations to be exact? So the first thing that you want to do when you have a differential equation, probably originally written in the form y prime is equal to some arbitrary function of x and y, is to write it in this particular structure. In particular, m times the differential x plus n times the differential of y is equal to 0. And keep in mind, if you have this particular structure, you can always write it in the y prime form or vice versa, because if we divide both sides by dx, we can have that y prime is just going to be equal to minus m divided by n, right? So if you have an fxy, you can easily identify what your minus m is and what your n is from that. Okay, so once you have identified these functions m and n, then what you're going to do is you're going to take the partial derivative of m with respect to y, right? So sometimes people abbreviate it with subscript differential variables. And then you're also going to take the derivative, the partial derivative of n with respect to x. Some people will write it as n subscript x. And if these two partial derivative functions are equal to each other for all variable values x, y in their associated domain, then we say that differential equation is a first order exact ordinary differential equation. And if my and nx are not equal to each other for all xy, then we say that that differential equation is a non-exact differential equation. So let's just look at a quick example to see if we can identify, is it exact or is it not exact. So let's give a very basic one. Let's consider 2y squared minus 4x plus 5 times the differential of x plus minus 4 plus 2y minus 4xy times the differential of y is equal to 0. So in order to sort of keep your mind in the same exact realm in terms of consistency, if you want to sort of get this little machine style approach of solving this, the first thing you want is a function times the differential of x plus some other function times the differential of y. Once you have it in this form, what you're going to do is you're going to name this first function m, and the next function you're going to call that m, right? So this is your mxy, and then this is your nxy. Now you're going to test the criteria in order to classify this as exact or non-exact. So the partial derivative of m with respect to y, so we're going to be treating x as a constant. So minus 4x plus 5 is a constant as far as y is concerned. So this is just going to be equal to the derivative of 2y squared with respect to y, which is just going to be equal to 4y. Now what we're going to do is we're going to take the partial derivative of n with respect to x. That means y is going to be a constant as far as x is concerned. So the derivative of minus 4xy with respect to x, y a constant, is just going to be equal to minus 4y. Now, although these two partial derivative functions do look similar to each other, they are not always equal to each other, because keep in mind, it has to be true for all xy. So these two expressions are not equal to each other, therefore this is a non-exact ordinary differential equation. Okay, so now we know how to identify a first order differential equation as either being exact or non-exact. So let's dive into a little bit of the theoretical background that's going to help us actually solve exact differential equations. So what we're going to do is we're going to begin by creating some function that's going to be relating to our actual solution. So let's assume that phi is a well-behaved function. Ideally continuous, ideally differentiable, ideally its derivatives must also be continuous, and so on. Usually continuous derivatives is usually a good place to start as well. So let's assume that phi is a well-behaved function, and let's also assume that it satisfies a couple properties. In particular, the partial derivative of this function phi with respect to x, let's assume that that actually is equal to mxy. And let's also assume that the partial derivative of phi with respect to y, let's assume that this is equal to nxy, right? So this function phi is a well-behaved function. Its partial derivative with respect to x is m, and the partial derivative of phi with respect to y is m. Okay, so let's assume that phi has this structure, and then we can see, okay, well, what type of function phi actually makes this true, and then we'll sort of bring that back into the conversation of exact or non-exact. Now, if it has these two properties, what we can do, assuming that m is continuously differentiable with respect to both x and y, is we can take the partial derivative of phi with respect to y now. So in terms of second order partials, we're going to take the derivative of x first and then the derivative of y next. So if that is the case, that means this is just going to be equal to the partial derivative with respect to y of mxy, which we can just simply write as just my. Right? So we have this particular expression, and what we can do for the other one is take the partial derivative with respect to x of that. So the partial derivative of phi, first y, then x. So this is going to be equal to the partial derivative with respect to x of nxy, which we can just simply write as nx. Okay, so let's assume that that is the case. So since phi is well behaved, and if it's well behaved via the criteria that is specified earlier, that means the partial derivatives are also continuous, right? So from that, we can use Clairaut's theorem for multivariable calculus and say, okay, since phi is well behaved, in particular, its partial derivatives are continuous in both x and y, that means the partial derivative of phi with respect to xy and the partial derivative of phi with respect to yx, i.e. you change the order, they're always going to be equal to the same exact function. Right? So if that is the case, then from these first two purple boxes, we can then classify that my must equal to nx. Okay, and simply, you can also follow this logic backwards and see, okay, well, if my is equal to nx, that means our differential equation is an exact differential equation. Maybe we can construct some function phi that is related to these solutions. So let's see if we can somehow connect this function phi, because obviously it does have some connections with our m and our n for our potentially exact differential equation. And let's see if we can actually solve for y, the actual solution for that differential equation. All right, so now here's the big part. So consider an exact differential equation. And let's again write it in the form mxy dx plus nxy dy is equal to 0, and since it is exact, we know the partial derivative of m with respect to y and the partial derivative of n with respect to x are going to be equal to each other. And let phi be a well-behaved function with the partial derivative of phi with respect to x is equal to m, and the partial derivative of phi with respect to y is equal to m. So using this differential equation here, what can we say? Well, m is just another way of saying phi x, so we can write that here. So we can write that as the partial derivative of phi with respect to x times dx plus the partial derivative of phi with respect to y dy is equal to 0. And we can slightly rearrange this expression by dividing both sides by dy. And you're going to have the partial derivative of phi with respect to x plus the partial derivative of phi with respect to y times the total differential of y with respect to x that's all going to be equal to 0. So you should recognize this expression from multivariable calculus as just the multivariable chain rule of a function f that contains two or more variables, in this case two variables x and y. So if that is the expression that we have here, notice that the total differential under consideration in this case is x. The function that we've sort of decomposed into x and y is the function phi, and therefore this is just another way of writing that the total derivative of phi with respect to x must be equal to 0. So, if the total derivative of a function phi, and keep in mind phi is a function of both x and y, and the total derivative with respect to x is 0 everywhere, that means phi of xy must be equal to a constant function. Right? Now, it's very important to notice here that this function phi does not contain any derivatives of y, right? So this is just an expression with x and y, not y prime, only, right? And if it's an expression with y in it, and it's related to our original differential equation that had y prime in it, that means that phi xy is equal to c. This is our implicit solution to our exact differential equation. Isn't that interesting, right? So we somehow construct this function phi, and if it satisfies those properties, then it must be a constant function, but that function contains that variable y that satisfies the original differential equation. Therefore, this would be our implicit solution. So we sort of went in a very convoluted way, I guess you could say, in order to construct that solution. Not in a direct manner, but more so in an indirect manner. Right? So if that is our implicit solution, then what exactly could we get from that? So before we dive into a couple examples to sort of illustrate this idea, I just want to make a couple points clear before we move forward. So if the partial derivative of phi with respect to x is equal to mxy, which is one of the properties we assumed phi has, then what would phi of xy be equal to in terms of m? So obviously we would take the antiderivative of mxy with respect to x, and then we would put some arbitrary constant at the end. But keep in mind, we took the partial derivative with respect to x, therefore if there's just a y term sitting alone, that would also differentiate off to 0 as well. So it's not a numerical constant necessarily, but it's going to be a function of y as the constant, right? Some people will use c of y, but that's going to be our constant. So that's our constant. Not really a constant, but it's a constant with respect to the partial derivative with respect to x at least, right? And similarly, for the other criteria that phi has, if we take the partial derivative of phi with respect to x which was assumed to be equal to nxy, then the partial derivative of phi with respect to no variables is going to be equal to the integral of nxy with respect to y plus some constant, but that constant would be something like g of x. Because keep in mind, this is a constant with respect to the partial derivative with respect to, that should be y. That should be y, right? With respect to the differential of y. Right. So here we have a bit of theoretical background for exact differential equations, which may seem a little bit strange at first, I guess you could say. So let's actually work through a couple examples of exact differential equations and sort of see how this theory actually gives us those solutions. So to start, let's consider this differential equation y minus x cubed times dx plus x plus y cubed times dy is all equal to 0. So if you notice, if we want to solve this with exact differential equations, it's definitely in the appropriate form. There's our m, there's our n, make sure m is associated to dx and n is associated to dy, and make sure you have 0 on the right hand side, and make sure the interior sign is a plus sign. But if you don't know how to use exact differential equations to solve, then you probably want to sort of rearrange this into as like a linear, because this is a first order differential equation, maybe this is a first order linear, maybe it's separable, maybe it's something easy, maybe you don't want to use exact differential equations to solve this, right? So let's actually just rearrange and just analyze what we have going on here. So if we divide both sides by dx and just rearrange things a bit, what we're going to have is y prime plus, we're going to have y over x plus y the quantity cubed plus, actually not plus, but equals x cubed over x plus y the quantity cubed. So we're like, okay, well, it's obviously a first order differential equation. It's definitely got a nonlinear term on the bottom. So this is a non-linear differential equation, which is definitely poses a potential difficulty. And moreover, it's not a Bernoulli equation, which we know how to solve, or a Riccati equation, which we at least have some idea of the structure of those solutions. So it's nonlinear, non-Bernoulli, non-Riccati. So you're like, okay, well, I don't have any methods to solve because I can't really separate this because, because of this term on the right-hand side. So that's problematic, right? So you're like, okay, well, let's give this exact differential equation structure a try, right? So let's see if we can solve this via the theory we have just proven. So y minus x cubed dx, x plus y cubed dy. So this is our m, this is our m. So the partial derivative of m with respect to y is going to be equal to 1, quite easy. The partial derivative of m with respect to x is equal to 1. They're equal. Therefore, this is an exact differential equation. Okay, so if it's an exact differential equation, how are we going to solve it via this theory that we've established? So that means there exists some function phi, which is going to be a constant, but we're not going to use that quite yet, such that the partial derivative of phi with respect to x is equal to m, and the partial derivative of phi with respect to y is equal to m. Let's focus on the phi x is equal to m first. You could do the phi y is equal to n first, but I like the phi x is equal to m approach first, but it doesn't really matter. Okay, so the partial derivative of phi with respect to x is equal to m. And remember, m was equal to y minus x cubed. So if that is equal to the partial derivative of phi with respect to x, what is phi of xy equal to? So we're just going to integrate that with respect to x. That's going to be equal to xy minus 1/4 x to the power of 4 plus some unknown function of y. We don't exactly know what that function f is equal to, but maybe from this second criteria we can figure it out. So using this phi that we have developed from phi x is equal to m criteria, let's take the partial derivative of that phi with respect to y. So if we take the partial derivative of that function, this one right here, with respect to y, so I'm sort of ignoring the equals n portion at the moment, that's going to give us x plus the derivative of f with respect to y, right? Now, keep in mind from the criteria of our function phi, that is also equal to m, right? And n, keep in mind, was equal to x plus y cubed. And we have this particular relation that should allow us to see what our f prime y is equal to. Because notice that these x's do cancel, and we have that f prime y, which keep in mind is the total derivative of f with respect to y, is equal to y cubed. And if we integrate both sides with respect to y, we're just going to have that fy, which is just a single variable function of y, is going to be equal to 1/4 y to the power of 4. You could put your c there, but we're just going to combine it with the arbitrary constant c at the end anyway, so I'm just going to leave it off for now. So that means our function phi, so let's bring that back again, was equal to xy minus 1/4 x to the fourth plus our function of y, which we now have 1/4 y fourth, and that's going to be our expression. Now the only way that this function phi satisfies those three criteria, in particular the partial derivative of phi with respect to y is equal to n, the partial derivative of phi with respect to x is equal to m, associated to an exact differential equation, is if this relation is constant. right? That's the only way it can satisfy those properties. So if that is the criteria, that means xy minus 1/4. Actually, what I want to do is multiply both sides of this equation by 4, because I really don't like those fractions. But, you can keep them if you really want. So we have 4xy minus x to the fourth plus y to the fourth is equal to k, is the implicit solution. Solution to the exact differential equation. And if you know, and you definitely should know already how to, you should be able to take the implicit derivative of this expression and verify that it is actually a solution to that original differential equation, which is actually pretty nice. Let's do another example of solving exact differential equations using this implicit method, but let's consider a differential equation that you probably wouldn't even try to solve in any other way, mainly because we have this sine y and cosine y term, which automatically tells us that this is indeed a nonlinear equation that is definitely not Bernoulli or Riccati. So the first thing that we want to do if we want to apply the method of exact equations is to get it in the standard form, right? And also keep in mind we do have this initial condition, so we shouldn't have an arbitrary constant c at the end. We should be able to find what particular constant c makes that initial condition true. So once we have that, what we're going to do is we're going to move this dx term to the left-hand side. Once we do that, we're going to have minus e to the y minus cosine x cosine y dx. And then we're going to leave that left term alone. So we're going to have sine x sine y minus xey dy is equal to 0. So once it's in this form, this is going to be your m, and keep in mind that has to be associated with dx. And this term right here is going to be your n, and keep in mind that has to be associated to dy, assuming that you have set this thing equal to 0. And now we need to check the criteria to see if this is indeed a exact differential equation. So the partial derivative of m with respect to y is going to be equal to minus e to the power of y. The function of y in the second term is going to be cosine y. The derivative of cosine is going to be minus sine. That's going to change that minus to a plus sign, and then you're going to have plus cosine x sine of y as your partial derivative of m with respect to y. Now we're going to take a look at this next function, and we're going to take the partial derivative with respect to x. So the derivative of sine is going to be equal to cosine, so we have cosine x, sine y is just a constant, and e to the y is just a constant as far as x is concerned, and that's just a linear term as far as x. So we're just going to have minus e to the y as that expression. And you look at these two expressions and see, are they the same or not? And indeed they are. Therefore, we have an exact differential equation. So since it is an exact differential equation, that means there must exist some function phi xy that is eventually going to be equal to a constant, such that the partial derivative of phi with respect to y is going to be equal to, what is it going to be equal to? That's going to be equal to m, and the partial derivative of phi with respect to x is going to be equal to m. One way you can sort of remember this, if you've remembered the first thing, i.e. my is equal to nx for exact, phi y is not m and phi x is not n. It sort of changes functions of reference, right? So instead of my is equal to nx, here we're looking at phi y is equal to n, so it's a little different, right? So again, it doesn't really matter which function you focus on, but I'm going to focus on, let's do partial derivative of phi with respect to x is equal to m again. Okay, so if that is the case, that means the partial derivative of phi with respect to x is equal to our m. So our m was minus e to the y minus cosine x cosine y. And then I'm going to integrate with respect to x. So the partial derivative, the zeroth derivative of phi will be equal to minus x e to the y. Derivative of sine is cosine, so we're going to have minus sine of x times cosine of y, and if we take the partial derivative with respect to x of a function of y only, it will disappear, so we have to include that there. And now, instead of doing the partial derivative with respect to x, now we're going to take the partial derivative of phi with respect to y. And keep in mind the partial derivative of phi with respect to x, this was equal to m. The next one's going to be equal to m. So this is going to be equal to what? So the derivative of that term is going to be equal to minus x e to the y. Derivative cosine is minus sine, so we're going to have plus sine x cosine y plus the total derivative of f with respect to y. And remember, this is going to be equal to n. And n was equal to, what was our n? N was sine x sine y minus xey. So we have this particular equation here. Notice that we do have a minus xey on both sides, so they cancel. We have a sine x cosine y on both sides, so they cancel. So what are we left with for that f equation? So we have f prime y, which again is the total derivative of f with respect to y, is equal to nothing, which means that f of y is equal to just some arbitrary constant. Let's just call it, for example, C1. Okay. So that means what? So that means our function of y, once we go back to our previous equation, is going to be equal to minus x e to the y minus sine x cosine y plus our function of y, which is just c1. And the only function phi that satisfies all of these criteria is if all of them are equal to some constant c. Let's actually just call it c2, and then we'll combine all of these constants together at the end. So therefore, what is going to be our general implicit solution? So our general implicit solution is going to be equal to minus x e to the y minus sine x cosine y is equal to some arbitrary constant c. Alright, so that's the hard part. Now we just need to figure out what constant c allows us to find our particular solution for this initial condition. Alright, so when x is equal to pi over 2, keep in mind this is going to be x and this is going to be y, what are we going to be left with? So x is pi over 2, y is 0. So that means this term is going to be equal to 1. This term is going to be equal to minus pi over 2 times 1. And then we're going to have minus sine of pi over 2 cosine of 0 is equal to c. Cosine of 0 is equal to 1. Sine of pi over 2 is equal to 1, so this term is just equal to 1. So we have that c is going to be equal to minus pi over 2 minus 1. So that is our arbitrary constant c. It has two negative signs. Our original function had two negative signs on the left. So we could actually make this particular solution very, very nice. So this is our implicit particular solution. So our implicit particular solution is going to be equal to x e to the y plus sine x cosine y is equal to 1 plus pi over 2. And again, this equation, if you just want to find an explicit solution, notice that our y is hanging out in our e, and we also have a y hanging out in that cosine, so definitely this is a non-elementary function in terms of solution, so it has some very weird patterns. But that is how you can use the method of exact equations to solve a nice large class of nonlinear differential equations, which is very, very nice. So the next question that might be on your mind is, okay, I have this first order nonlinear differential equation. I've got my m, I got my n, but my and nx are not equal to each other. Is it possible that we can make it an exact differential equation even though it's not exact to start with? And is it always possible that we can solve or find this, magical integrating factor like we did for first order and homogeneous equations? Can we always make it exact? Like that would be a very important tool. Right, so we're going to approach this just like we did for first order linear and homogeneous differential equations. So what we're going to do is we're going to seek a function f, and f could be a function of x, it could be a function of y, it could be a function of both of them, but I'm just going to call it f for now, such that the following differential equation, fm dx plus fn dy equals 0 is exact. right? I.e., we multiply both sides of the equation by our non-exact differential equation by f, and then we get an exact differential equation. Then we can apply that theory and then be done with it. So what does this function f look like? Well, we have a closed form for it for our first order linear inhomogeneous. Maybe we have some closed forms for this f in this case as well, right? So if this exact, well, what exactly structure does this function f satisfy? So that means the partial derivative with respect to y of fm will be equal to the partial derivative with respect to x of fm. So this is like our my is equal to nx, but this is our new m and this is our new n. All right, so let's apply the product rule on both the left and the right of this equation. So we have the first times the derivative of the second plus the second times the derivative of the first is equal to the first times the derivative of the second plus the second times the derivative of the first. Right? So we have that particular relation. The next thing I want to do, since we're solving for f, is to move our f's to the same exact side. So once we do that, we're going to have f times my minus nx is equal to nfx minus mfy. Right? So once we have this expression, then we have, I guess you could solve both sides of this equation for my minus mx. You may think, okay, well, why would I want to do that? You'll see maybe in just a moment. So we're going to have nfx minus mfy all over f, because that's everything with f in it, is equal to my minus nx. Now, keep in mind, if the original differential equation was exact, then my and nx are going to be equal to each other, and the left-hand side of this relation is just going to be equal to 0. Right? And then you don't really have to find such an f, right? But we're assuming that this expression is not equal to 0. What f would that be equal to? Now, notice what we have here. We're trying to solve for f here. We know what m is, we know what y is, therefore this is known to us, but we don't know f is, and f is a function of two variables. So therefore what we have here is a partial differential equation in f. Right, because we have the partial derivative with respect to x, y, and the original. So this is a PDE, right? It's going to be a linear, actually, yeah, this is going to be a linear PDE, but nonetheless, it is not easy to solve, right? So let's see if we can look at a couple special cases for this PDE, and let's see if we can solve those on case by case. So case 1. Let's assume that our function f is a function of x only, implying that the partial derivative y of f will be equal to 0. What does our special PDE reduce to? So we're going to have my minus nx is equal to, so fy is equal to 0, so we're just going to have n divided by f times fx, and then we can solve this equation for f, or at least we have a differential equation, an ordinary one, in particular of the form df divided by f is equal to my minus nx all over n dx. Now, keep in mind, if f is a function of x only, that means the right-hand side of this pink equation is also going to be a function of x only. And in particular, this is a separable differential equation, and we can solve it exactly. So in this expression, we have that f of x is going to be equal to e to the integral of my minus nx divided by n dx. So that is what our integrating factor that will make our non-exact an exact differential equation. So that's a very important relation. But how do we know if f is a function of x only if we don't know what f is? Keep in mind, from this relation we can get the following statement. So f is a function of x only if and only if my minus nx over n is a function of x only. I don't care what that function is, but if it's a function of x only, then that means that f is a function of x only as well. And we get that sort of a relation from this pink and orange boxes in the statement above. right? So how can we know that our integrating factor is a function of x only? We analyze this particular relation here and see if it is or not, right? So that's the first case for this PDE. Let's look at another case. So instead of assuming that the function is a function of x only, let's assume that the function is a function of y only, implying that the partial derivative with respect to x will be equal to 0. So if that's the case, that means my minus nx would be equal to minus m over f times the partial derivative of f with respect to y. And then we can translate this into a separable differential equation, in particular df divided by f is equal to nx. I'm just going to reverse this to get rid of that minus sign. So nx minus my divided by m, and that's going to be multiplied by dy. And the dy is coming from that fy term. Right, so we can solve this differential equation for f exactly. So we're going to have that f of y, because it's a function of y only, will be equal to e to the integral of nx minus my divided by m dy. And that would be the structure of our integrating factor if our integrating factor is a function of y only. But again, how do we know if our function is a function of y only if we don't exactly know what that function is? So keep in mind, f is a function of y only if and only if nx minus my divided by m is a function of y only. Therefore, all the x's should eliminate and disappear from that expression. Right? So we have my minus nx over n as a function of x only, and we have nx minus my over m for being a function of y only. And if it's not a function of x only or a function of y only, that means it's a function of both x and y, and the expression therefore relies heavily on the solutions of that original partial differential equation, right? So what would case 3b. So case 3 I'm actually just going to state as a theorem because from here on it gets a little bit more complex. So if m dx plus n dy is equal to 0, this particular equation, if this is a non-exact differential equation, and let us also assume it has a general solution. In particular, it's going to have a solution phi xy is equal to c, has that particular structure. If that is true, then there always exists some function f, generally speaking, being a function of x and y, such that mf dx plus nf dy equals 0 is exact. So there always exists some function of both variables at the most such that you can multiply by this non-exact equation and obtain an exact equation and then solve. But as far as what that function is, it's really hard to say, and it possibly is not even a function you've ever even seen before. But it exists. At least that much we can guarantee. I won't prove this theorem here. It's actually not too hard if you give it a try. But at the least, we can take this theorem as a peace of mind, I guess. That is, as long as the solution for this exists, you can always solve it via exact differential equations, provided that you can find that integrating factor, which most of the time you can't. So there's a bit of a theory for us to think about. Let's go through an example of a non-exact differential equation and see if we can go ahead and make it exact and then solve it. So let's consider this first order nonlinear differential equation and see if we can come out with a solution for it. So what we have here, and let's actually, I have a slight misprint, that should be dx. Let's see if we can see if this is exact or not. So we have our dx first, so therefore that's going to be our m, and we have our dy second, therefore that's going to be our m. So if we take the partial derivative of m with respect to y, that's going to be equal to 0, and the partial derivative of n with respect to x is going to be equal to e to the x cotangent y, and the rest of that doesn't have x in it, so that's all you get. So we have nx here, my here, and they're not equal to each other. Therefore, this is a non-exact ODE. Right? It's not Bernoulli, it's not Riccati, it's not linear. Therefore, at least up to the present time, we don't have any methods to solve it. So if it's a non-exact ODE, at least from that theorem we stated, there always exists an integrating factor, but the problem is finding it, right? But at least we have two methods of deciding what that function is if it happens to be a function of x only or a function of y only. So let's at least just look at those cases and maybe we'll be lucky. So case 1, let's consider the function my minus nx over m. So if this is a function of x only, our integrating factor is 2. And we also know its structure if that is the case. So my is going to be equal to 0, nx is going to be e to the x cotangent y, and n is going to be e to the x cotangent of y. Right? So we have this particular expression. So is this a function of, oh, that's not my n. Our n is plus 2y cosecant y. I was like, wow, that would be actually very, very nice, right? So that is our my minus nx over n. So do all of those y terms cancel? If you do some trigonometric manipulations, you'll realize it's not. So this is not a function of x only. And if it's not a function of x only, that means f, our integrating factor, is not a function of x only, right? So that's a sad thing. So let's just hope that it's a function of y only. So case 2. So we need to analyze nx minus my over m, and hopefully this is a function of y only. Keep in mind our function m was actually the nicest of the two functions, so hopefully we're lucky here. So nx is going to be e to the x cotangent y minus my, which is going to be equal to 0, all over m, and our m was just equal to e to the x. So if we do some simplifications, what we have here is e to the x cotangent y divided by e to the x, and notice that these e to the x terms cancel, and we're just left with cotangent of y, which does have y only. That should make you happy, right? So if that is the case, that means that our integrating factor is a function of y only, right? And if it is a function of y only, it actually has the structure e to the integral of nx minus my over m dy, right? Which is just going to be equal to e to the integral of that function that we were left with, the cotangent of y. Right, so that is going to be our integrating factor, and we should know that the integral of cotangent is just going to be e to the natural log of sine of y, which just simplifies to the sine of y. So that is our magic integrating factor. So let's go back to our original differential equation, which was e to the x dx plus e to the x cotangent y plus 2y cosecant of y dy is equal to 0, and let's see if we can make this non-exact equation an exact equation. So our integrating factor is sine y, so we're just going to multiply both sides of this non-exact differential equation by sine y. Once we do so, we're going to have sine of y e to the x times dx plus, and then cotangent is the same as cosine over sine, so those signs cancel. So we're going to have e to the x cosine of y, and then plus, keep in mind cosecant is 1 over sine, so 1 over sine and secant are the same, so we're just going to be left with 2y there, and then we're going to have dy is equal to 0. So now we have a new, potentially exact differential equation. So let's see if it is indeed exact or not. So we have our m here, which is associated to dx, our n, which is associated to dy, and let us hope that my and nx are equal to each other. So the partial of our new m with respect to y is going to be equal to cosine of y times e to the x, and the partial derivative of n with respect to x is going to be equal to e to the x cosine y, and the derivative of 2y is just 0, so we're just going to be left with e to the x cosine y, and notice that they are the same. Therefore, we now have an exact ODE. Sometimes without looking at the cases, or even if both of the cases don't work, sometimes you can fiddle around and multiply both sides by some random functions, and maybe you'll get lucky and make it an exact differential equation. So if you're good at guessing what that f might be equal to. Right, but now we have an exact differential equation, so we can apply the same theorem. So that means there exists some function phi such that the derivative of phi with respect to x is equal to m, which is equal to e to the x sine of y. And if that is equal to that, then that means phi xy, so integrate with respect to x, is going to be equal to e to the x sine of y plus some arbitrary function of y. And then we're going to take the partial derivative of phi with respect to y, and that's going to be equal to m. So we're going to have e to the x cosine of y plus f prime of y, and that's going to be equal to n, and our new n was e to the x cosine of y plus 2y. Now we just need to figure out what that f is, and notice that this e to the x cosine y do cancel out, and we're just left with f prime y is equal to 2y, which means that our function f is just equal to y squared. Once we have that, then we have that phi xy is equal to e to the x sine of y plus our function of y squared, and we already know that the only way that this can be our solution is if phi is equal to a constant. Therefore, this right here in this little pink box is our implicit solution to our original non-exact differential equation. Right, so definitely a lot of algebraic trickery associated to exact and also non-exact differential equations, but it definitely gives us some insight that regardless of the first order differential equation, whether it be linear or nonlinear, we always do have some hope of finding that solution, provided that the solution even exists. I hope you enjoyed this video, and I'll see you in the next one. Take care.